conditional probability and the events A and B. All right, so we draw a dard. We draw a card from a deck, and we do not replace it. And then we draw a second card. First, the A is the first card is a heart. B, the second card is a heart. What's the probability of the first card being a heart?
1 out of 4.
1 out of 4, 13 out of 52. I'm going to use 13 out of 52, so we reinforce the number of cards in the deck. But it's the same thing.
Okay. It's probably like common denominator too. Makes it easy.
There you go. How's that? Yeah, it usually is when you're doing the math. Okay. Why can we not determine the probability of B? So the probability of A, we draw a heart. And then we want to know the probability of B, we get a heart again. I don't know.
Oh my god.
How many hearts are going to be left in the deck, depending on what happens in A.
Exactly. If you draw a heart on the first card, that changes the probability of the second one, right? So you have to know what happened first. So, is that what you're going to say, Humor?
I just said that it's contingent on the first one.
Same thing. Probability changes if first card equals heart.
No.
There you go.
Oh no.
Okay.
Wait, that's actually kind of
So,
bad.
these are called dependent events. All right? All right. Number 2. If you draw, same thing, except we replace the card now. So we draw it from the deck, we put it back in after we do that. What's the probability of getting a heart on the first one? 13 out of 52, that's the same. What's the probability of a heart on the second one? Same thing, 13 out of 52, because we put it back in. So these are independent events, okay? Okay, so tell me if these are dependent or independent. Rolling a 2 on a die and tossing a coin in the air. Those are going to be independent because they have nothing to do with one another, right? B, we're choosing 2 cards without replacement from a standard deck. First card is a king, second card is also a king. Those are dependent, right? Because if you draw a king on the first one, that changes the probability of the second one. 2 cards with replacement. As soon as it says with replacement, you know it's going to be independent, right? Because you've put it back in and reset everything. So it's independent. Okay. All right. So, boom. So now a bit of notation. So the probability that we draw a heart, we're going back to the very first one, it's 13 out of 52 or a quarter. So this symbol here, probability of B with the little line and then A, is called the conditional probability of event B. So it says the probability of B happening given A has already happened. Okay? So probability we get a heart given that we already drew a heart. So what's the probability of getting a heart on the second card? 12 out of 51. Right? Because there's one less card in the deck. What does it mean when you have a little line above the thing? It's not been met. It's called the complement, right? So this means the probability of getting a heart given we did not draw a heart. So how many hearts are in the deck?
13.
Out of how many cards? 51, right? Because it's the second card that we're drawing. So if we draw a heart in the first one, the second card probability of getting a heart is 12. If we don't draw a heart, it's 13 out of 51. Okay. We do our dice thing again. You roll them, blah, 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 blah. There's all the combinations. Event A is the sum of the two dice is 10. What are the combinations that will add up to 10 by rolling the dice? 4, 6, 5, 5, and 6, 4. Event B, the number of each die is the same. Yeah. So there's 6 of those. Okay. What is the event A and B? They're in both of these. 5, 5 is the only one. Okay. What's the probability of A happening? 3 out of 36. There's 3 things in A. There's 36 total combinations. So 3 out of 36. And 1 out of 12 if you want to reduce it. What's the probability of B happening? So 6 out of 36, which if you reduce it is 1 out of 6. What is the probability of B happening? So the number on each die is the same, given that A happened. The sum of the two dice is 10. So, all the options for this one are here. There's only one where they have the same number, and the total possible for getting the same number is 6. So it's what? It's 1 out of 3. Right? Because the total number of ways that A can happen is 3. So these are your choices. There's only one choice in there that fits this one. Okay? So it's 1/3. What's the probability of A happening given that B happened? So we rolled doubles. What's the probability that the two dice add to 10? 1 out of 6. Because we've narrowed the probability, we said this has already happened. The probability of it adding to 10, there's only one of them, 5. What's the probability of A and B happening? Well, it's A and B. So which one of these is in here? There's only one of them, right? What are the total combinations? 36. All right? The probability only gets smaller when you start putting in these little, given that something has already happened, right?
Rolling the dice once.
Well, you're rolling each dice once, yeah.
That makes it make more sense.
What's the probability of B and A happening? Same thing. 1 out of 36. Okay. We're not going to verify that. Don't worry about that. Flip the page. We get another formula. Yay. All right, so if events are dependent, the probability of A and B happening is the probability of A times the probability of B given that A has occurred. Okay? Yeah, I will give you this formula. You don't have to memorize it. If they are independent, what is that? What? Okay. Why do I have this thing? If in the,
Okay, why is there a black cloth at the top right?
I don't, what is going on? Let's just close this. And then, okay, if independent, then the probability of A and B equals if they have no relation to each other, then the probability of A and B occurring is just the probability of A times the probability of B. Okay? If they're dependent, you have to use this formula. All right. Back to cards. Oh, and these formulas, as you'll see, I stay away from them unless you're given this information. Things like this, if you just think about it, you can do it without using these formulas. Okay, so cards. So, we're drawing 2 cards without replacement from a standard deck of 52 cards. Determine the probability of the following events. Okay. Both cards are red. So what's the probability of the first card being red? 1 out of 2 or 26 out of 52. What's the probability of the second card being red?
25 out of 51.
That was a replacement. Oh, without. That's crazy. Wait, mine says. No, I'm reading the wrong one.
Okay. All right. So probability that both cards are red, 26, and then 25. Pretty straightforward. I'm not going to do the multiplication. Neither card. What? Okay. Okay, yeah. It doesn't matter. Neither card is a club. So, sorry? There's 39 cards in the deck that are not clubs. We're not replacing it. So you reach back in. How many non-clubs are in the deck now? 38. How many cards are there? 51.
That's not too bad. You just do your cross multiplication, just like
You do not cross it.
Okay. First card is a king. The second card is a 5. How many kings are in the deck?
4.
4. So the probability of getting a king on the first one. How many 5s are in the deck?
4.
How many cards are left in the deck? 51. All right. One of the cards is a king, and the other is a 5. So that means you can do this. You can do king on the first one and 5 on the second, or 5 on the first and king on the second.
So you pretty much just times the thing, the last one, that's it.
Pretty much.
The first and second options the same.
They will be, yeah. But you have to double it. That's the point here. So, probability of getting a king. Okay, we just did it, right? 4 to 52, 4 to 51. Or you could flip the order, which is the same numbers, right? So the whole point here is the probability doubles if you don't require the order. Right? As soon as you restrict it to the first card has to be a king and the second card is a 5, you've eliminated this option, right? So if you take away the order, then you increase your probability. So when you add order to things, it shrinks the probability because you're putting more restrictions on it. Okay. There's the multiplication law for independent events that I just showed you. If they're independent, you can just multiply the individual probabilities. Okay, now we're drawing with replacement. This is the easier version. Both cards are red. What's the probability of the first card being read?
Half.
Half, or 26 out of 52. What's the probability if you replace it of the second card being read? Sorry? 26 out of 52. They don't change.
Why is it still 26? I thought it was 2
Wait, you replaced it.
Oh, with replacement.
Oh my gosh. All right, so you get a 4. Okay. First card is a king, second card is a 5. 4 out of 52, 4 out of 52. One of the cards is a king and the other is a 5. So I've taken away the order, right? So you can do it both ways. Plus, and then you flip the order. So it's the same numbers. You can just multiply by 2. Comes higher. Because I haven't restricted the order, right? Yeah. Okay. Okay. Mutually exclusive and independent. So what does mutually exclusive mean again? Yes, they can't happen at the same time, right? That's the Venn, if you think of it, it's easier when people see the Venn diagram. Mutually exclusive means the circles don't overlap. Right? Me. NME means there's an overlap here. As soon as there's an overlap, they're not mutually exclusive. Okay, so this is where we use the formulas here. Are these events mutually exclusive? So, if they're mutually exclusive, then that means the probability of A or B. I'll give you the formulas, but this was the formula yesterday. Equals that. That's the definition of mutually exclusive, right? Because there's no P, A, and B. So, we know the probability of A or B is 3/5. We know the probability of A is 1/3. Probability of B is 2/5. If you do that math, you're going to get 3/5 equals 11/15. Are those the same thing? No, they're not. Therefore, they're not mutually exclusive because there is some factor that we have to calculate. Probability of A and B, right? Because if this is 0, then it's this case. But because these don't add to this, there is a number there. So the first thing we have to do, well, in the next question, it says, are they independent events? Okay. So what's the definition of independence? Yeah. So, if they're independent, probability of A and B, this is really big, equals probability of A times probability of B. Well, we know what the probability of A and B are. It's 1/3 and 2/5. So 1/3 times 2/5. We get 2/15. So what we have to figure out is, what is this? Well, we can calculate that because we know this, right? We know they're not mutually exclusive. So there is this, and we solve this, this, and this. We're given all those. So we can figure out this, right? So we can sit.
So it's gonna be the same number?
No, it won't be the same number. Oh, sorry. Well, yeah, this is all part of one question, right? They've given us all this information, so we prove that they are not mutually exclusive. There is some overlap between them. So we just have to find that overlap. Once we know that, then we can determine if they're independent
Oh,
because we know this now,
right.
right? So we're trying to find this that we can plug in there and see if it equals 2 over 50. So really, over here, I can just take this stuff and go 3 over 5, which is this. I've added those two together. All right? I did that here. That gave me 11 over 15. But we know that there's some of this there. So I go minus probability of A and B. So you just have to solve for probability of A and B. So if you do that math, you will end up with 2 over 15. And since that equals that, they are independent events. That make sense? It's a bit formula-esque, I guess. I don't know. Okay. Probability of A is equal to half. Probability of B is equal to a third. Probability of A and B is equal to a quarter. You like these? Find the probability of A given that B happened. So, if you remember the formula, which is on the previous page, it's this. Okay? I'll write it over here. So we're going to go probability of B and A happening equals probability of B times probability of A given B. And I just want to point out here, I'll put it back up in a sec. This formula can be rewritten, right? I have A and then B, so we have probability of A here, and then the second letter goes there, given that A has happened. So if I flip the letters here, I'll do it on here. If I write probability of B and A, that's going to be probability of B times probability of A given B has happened. Okay? So just be aware that you can flip those, right? And whatever letter's here is going to be the one there. So that's why I wrote it that way in this question. All right. What's the probability of B and A happening? It's the same as that, right? So we know that's a quarter. Probability of B is a third. And we're trying to find A given that B happened. So it's going to be 3 over 4. Is that okay? Should be able to do the second one now, because it's pretty much the same thing. B given that A happened, so that's going to be A and B equals probability of A times probability of B given A happened. Which again is a quarter. This time probability of A is a half. So we get 1/2 equals probability of B given A has happened. Probability A or B. What's the only formula you know for A or B? You only know one formula. That's the only formula. I mean, and then A and B could be 0. But you know these are not mutually exclusive because there's an A and B. Right? There is overlap. So you know they're not mutually exclusive. So you can use this formula. Probability of A, probability of B, probability of A and B. Plug them in, solve. Seven out of 12. Is that okay? All right, last question. The probability that Ashley will pass math is 0.7. Probability that she will pass English is 0.9. If these events are independent, what is the probability that she will pass math and English? So they're independent events. So what can you do with the probabilities? You can just multiply them together. So 0.7, 0.9 gives us 0.63. 63% chance she passes both.
That's
That's pretty good.
She's stuck.
I don't know, that's... What?
Those are not great.
Yeah, you're right, it's not
odds.
great. Okay. All right, math or English. Is this number going to be higher or lower? Should be higher, right? Because it's one or the other. Okay? Are they mutually exclusive events? No, because you can pass both, right? Which is what we just saw here. Right? So, the probability she passes math, 0.7 plus 0.9. And as soon as you see that, you know they have to be not mutually exclusive because 0.7 plus 0.9 is over 1. And you can't have a probability over 1, right?
160% chance.
Yeah. So you have to take away the overlap, which is that. This? Oh, yeah, that should be and. Thank you. So there's a 97% chance she passes one or the other. That's good.
That's good, but which one do you need to say?
Well, you need English
Need
12
English,
for...
So she should really be hedging her bets.
Okay. The probability she passes math, but she fails English. So. That's an and sign. That's just my really bad shorthand. Now, why did I put this over the English thing? It's the opposite, it's the complement, right? So what, and these are independent events. So if it's M and E, I can just multiply the probabilities. So the probability of math times the probability she fails English, which is the complement. Probability she passes math is 0.7. What's the complement of passing English? 0.1, right? There's a 90% chance she passes, or 0.9. So the opposite of that of failing, there's a 10% chance she fails, or 0.1. There's a 7% chance he passes math but fails English. All right. Neither math nor English. Well, there's two ways to do this. You can do the two complements. Not the first. What do you mean by the first one?
Like math and English.
Well, she's not passing either.
Yeah, so I'm saying if you have 0.63,
Mm-hmm.
take one and you subtract 0.63.
No, because this part here is like on a Venn diagram. That's not a Venn diagram. That's this part, right?
Yeah.
What does this represent?
Oh,
It represents all that stuff, right? So then what is this question asking?
everything that's
Yeah, the little bit that's out here. So you can either go, she fails math and she fails English, which is the complement of, so it's going to be 0.3 times 0.1, which is 0.03. Or you can go 1 minus the probability she passes math or English. So 1 minus 0.97, which is 0.03. So there's a 3% chance she fails both classes. How's that? That makes sense? Only use the formulas. I tend to only use the formulas if it's given to you in a situation like this, or specifically when they kind of directed you in that path. If it's a question where it's like drawing cards and things like that, I tend to just do it by thinking in my head. Okay? That is it. Oh, what do I want you to do? No. And so I promised I would do one, but. You can do number, well, you can see my work from last night. Let's do 1, 2, 3. You don't have to do 4. 6. You can do 7. Although those kind of tend to be the same. Okay, what am I saying? 1, 2, 3, 6, 8, 9, 10, 11, 12, 13, 14. So just don't do
I
4, 5, 7.
don't do 4, 5, or 7.
Not 4, 5, and 7. How's that?
Alrighty.
Look, I'm not checking it, but
It's so funny because I circle the questions as you're saying them, so then I'm like, it's like a journey to get to the final result.
that's my life.
Seriously, that book smells so bad.
The book smells
It
bad?
smells